Okay, so we're in day 2 of linear systems. We're kind of getting a shortened content since we don't have as many days this semester as usual, but I think we can get through the important pieces. So last time we defined what a linear system was, and we solved them using Chapter 3 and Chapter 2 methods. So today we're going to define a matrix, determinant, trace, matrix vector multiplication, and then we'll solve a homogeneous system of equations and write the solution in vector form. We're going to talk about what is e to the lambda t times v, because that expression plays an important role in what we're about to do. And then we're going to try to start solving x prime equals ax today using an ansatz. All right, so let's get started. Let me pause for a minute while I write down a system of equations. All right, so the following are equivalent notation. So here we have, on the left here, we have a system of 2 equations and 2 unknowns. And that is identical to writing this equation, where we have a matrix times a vector equal to a vector. In shorthand notation, we could write that as like ax equal b, where the matrix A is a, b, c, d, the vector x is xy, and the vector b here is ef. Okay? And so this is, writing it in this form defines the matrix vector multiplication. So just as a quick example, we might have something like 1, 3, 2, minus 1, times 2, 1. And how would we express that now? Right, so using our definition up here, right, that's a times x plus b times y, so that's going to be equal to 1 times 2 plus 3 times 1, right, and 2 times 2 plus minus 1 times 1. Okay, and so rewriting that, then that would be 2 plus 3 is 5, and 4 minus 1 is 3. Good. Similarly, right, if I were to write the system, 2x plus 3y equals 5, and x minus y equals 1, how would we express that in matrix vector form? Did you write it down? 2, 3, whoops, let's see if I can write my stuff here good. I'm starting to lose my voice tonight. 5, 1. Good. All right, so that is matrix vector multiplication. All right. Now, just a couple of quick definitions. We remember what a determinant is from Calc 3. So the determinant of a matrix A, say for example, let's just grab the determinant of the matrix that we just had here. 2, 3, 1, minus 1. Remember, the notation sometimes is just a straight line, but that's not the absolute value, right? That says determinant. And so we remember that that's 2 times minus 1, go kitty corner there, minus 1 times 3. Okay, so in this case we have minus 2 minus 3 is minus 5. Good. All right, I wanted to define one other thing, and that is the trace of a matrix. So let me say trace of a matrix A, B, C, D. It's going to be the sum of these diagonal elements. Okay, so it's the sum of the diagonal elements. And so for the 2 by 2, the trace of A is going to be A plus D. Okay, so for like a 3 by 3, you could still define it, right? So the trace of this matrix would be A plus E plus I. Good, and so on. Good, so that's called the trace. The trace is the sum of the diagonal elements. Good. Now, While we're on the topic of systems, we already know how to solve a system of equations, right? So we already know how to write the system. The system is solved by taking determinants. In this case, remember to replace the first column. And then we would have, let's see, A, C, E, F. Good. Now there's a couple of things we have to note about Cramer's rule, right? And that is that this works as long as the denominator is not equal to 0, right? That's what we were saying before. What happens if the denominator is 0? If the denominator is 0, then the system, do you know what happens in that case? The system represents what kinds of lines? Either parallel lines, in which case there would be no solution, or what's the other case? The same line. They would be multiples of each other. How many solutions would there be in that case? There's an infinite number of solutions. And this is the case that I wanted to talk about. How do we express the infinite number of solutions? And so an easy way to look at this is the homogeneous set of equations. So suppose I've got something like, let's say x plus 2y equals 0 and 2x plus 4y equals 0. Okay, now before we do anything else, let's go ahead and rewrite that in matrix vector form, just for practice. Good. And now, what do we notice about our determinant? Oh, maybe I should just use this notation. 4 minus 4 equals 0. And so therefore, you can just see right here, right, that these are the same line. They're multiples of the same line. So therefore, how many solutions do we have? Any pair xy that satisfies, that satisfies this relationship, x plus 2y equals 0, is a solution. And so that's a line through the origin, right? Now, how is there an easy way to write this line in vector form? In vector form. Well, notice that if you put in xy any multiple, now I'm going to do a little trick and I'm just going to swap these numbers and write minus 2, 1. I'm going to negate the top and just switch them. So I've swapped the numbers and negated one of them. Any vector of this form will work, right? Because if you plug in minus 2 for x, right, and a plus 1 for y, that would satisfy our equation. Good. And so this is the way to write the full set of solutions to this set of inequalities. Okay. And so the set is an infinite number of solutions, and we can write them in this form. Good. All right. Just out of curiosity, do we remember how to write a line in vector form? So in 2D and 3D, suppose we want to go through the line. Actually, this is true for any dimensions, but the line goes through point P in the direction of Q. Do you remember how to write the line for that? The line is written as P plus T times Q. Right, so think of it this way. If you're at time 0, for example, that would put you at point P. And then after that, you're going from P. So this would be like the vector P, or the end point of P. And this might be Q, the direction Q. And so this line then would be this whole thing, right? Good. All right. So I think we're getting close to time here, so I think we'll stop. And in the next section, we're going to take a look at systems of differential equations and see how we can solve those. So we'll be right back.